Welcome to Intelligent Systems, an introduction to artificial intelligence. In this video, we will look into unsupervised learning techniques which can shed light onto data without any training data necessary. Training data may simply not be available because it's difficult to generate. It may not be representative, it's may not be unbiased as is needed, and of good quality as needed. And supervised learning requires training data. In contrast, unsupervised learning does not. And there are two classes of algorithms for unsupervised learning: clustering, which groups similar items into clusters, and dimension reduction, which projects from high dimensional to low dimensional space. So let's exercise these two techniques on our own MNIST data, and let's do it manually. So these are the averaged digits per class, so the 0, 1, 2, 3, 4, and so on. And let's visually arrange the digit to reflect their similarities. So in trying to do so, we will think of some visual features like, for example, a vertical line which can be found in the 1, the 4, the 7 and 9, a curve at the top for 0, 2, 3, 8 and 9, and a curve at the bottom for 0, 3, 5, 6 and 8, and curves at bottom and top are in common for 0 and 3 and 8. So if we do that, we'll put the vertical lines into one group. Out of the ones on the vertical line, the 9 has a curve at the top, so it should be closer to the rest. The rest is all curvy, and curve at the top is here also at the top, curve at the bottom is here at the bottom, and those that have both are somewhat in the middle. And the 8 being here to the left because it's pretty close to the 9, the 3 being close to the 8, and so on. And nicely also with this layout, the 0 is on one end and the 1 is on the other end. So that would be my manual depiction of the relationships between the digit and our data. Now let's do it in a different manner by clustering. So we want to iteratively group the digits now by similarity. And according to my judgment, the 1 and the 7 are the most similar. 1 and 7, it's just that line that seems to be different. 3 and 5 are also very similar, so they get merged next. The 6 fits also quite nicely to those. And this way we create this hierarchical arrangement. Yeah, and those are essentially the two algorithmic approaches, or the two approaches to unsupervised learning. We do a layout in a two-dimensional space, or we group together, for example, hierarchically. And the two techniques are called dimension reduction and clustering. So now let's look into the major players of these techniques. For dimension reduction, there are essentially two main techniques: principal component analysis, PCA, and t-SNE, t-distributed stochastic neighbor embedding. The key difference between those two techniques is that PCA is a linear transformation, and it has complexity linear in n, the number of items that we have to deal with, whereas t-SNE is a nonlinear transformation and has complexity n square. So let's look into detail how these two methods work. Let's start with principal component analysis, and it essentially comes in 3 steps. First, we identify the major axes in the data. Then we rotate the data along these axes and center on 0. And to carry out the dimension reduction, we cut off minor axes. So let's do that for a simplified example in 2D. And we want to project into 1D. Now, this is our original data. And we could, of course, just project this data as is onto the x-axis. Right? This point would get here. This point would move there. Point over there would move here. But that is not a good idea because we do not maximize the variation on the x-axis as it is visible in the original data. That is the maximum length, and here it will be shorter. So that's why directly projecting is not a good idea. Instead, we want to find the major axes and then rotate along them. And we do that in the first step, and this is the major axis, and that is the kind of minor axis if we have a two-dimensional case, and correspondingly we would do that for more dimensions if we had them. So we sort them essentially by the variance that they carry. Now in the third step, we rotate our data and center it in the 0 point. So now the major axis is aligned with the x-axis, the minor axis is aligned with the y-axis, and the data is centered here in 0. And then finally we carry out the dimension reduction. We simply cut off the y-axis, all of the data gets projected onto the x-axis, and that is our final dimension reduction. So what is good about PCA? It's very, very widely used. It's out of the 4 techniques we cover in this lecture the most widely used one, at least in the life sciences. It has a complexity of n times d squared plus d to the cube, where d is the dimensionality of our vectors, and we have n of such vectors. The reason why we have this complexity is that the original data matrix X is of size n times d, and PCA first computes the covariance matrix. So for each vector n, we have a d by d calculation, so that means n times d squared, and then we compute the eigenvalues of this, and that takes d to the power of 3. Now usually we have many more data points than we have dimensions. So for example, in our MNIST data for digit classification, we had overall 70,000 images and we had 784 dimensions. We also learned that in supervised learning, you should have 10 times or at least 5 times the amount of training data as you have dimensions. So generally, this will be in most scenarios the case. So that means n is the dominating factor, and that means PCA is linear in n. Now, what are the cons of PCA? Well, the main con is that it's a linear transformation, and that means it cannot deal with non-linearity in the data. So linear transformation here does not now refer onto the complexity, but that it is basically a linear combination of all of the dimensions as being computed. And if we have data that is, for example, grouped by density and so on, then that cannot be handled by PCA. And what is important, it's a dimension reduction. That means we do lose information. So the high dimensional distances are not preserved in the low dimensional space, though they are preserved as good as is possible. So consider this point here and that point there. They have a distance as indicated by the red line. Now after projection, the distance is much shorter. So here you can see it, original distance, distance after projection. So of course we do make a mistake. And this error that we're making here for that specific example, that error is not evenly spread across all of the distances that exist in our data. A second aspect is that the first principal component may not be the most informative or interesting one. Now, that is not necessarily a disadvantage. We can also use it to our advantage. And let's consider practically what that means. Now imagine this was our data. Essentially, we have 2 lines here kind of, and there is a longer line and the dots are oriented along that long line and a shorter one over here. Now, if we apply PCA, then the major axis is this one, and after projection, the difference between those 2 lines has completely gone, because the second dimension, the minor axis, was separating that short line from the long line. Now, what is more interesting out of these 2 axes? The major axis that can explain all of the variance, or the minor one that was clearly separating 2 parts of the data? And in some cases, that second dimension will be the best one. However, this is easy to address, this problem. It just means in principal component analysis, do not just consider the principal components, but explore also the lower dimensions or the next dimensions. So if you have 2 dimensions for visualization, also plot the first against the third, the second against the third, the fourth against the fifth, and so on, and explore that. Maybe you see this aspect. But of course, the first 2 dimensions in a 2D projection from a high dimensional space carry the most variation of the data. And that is actually what this looks like for our MNIST digits. So here are 70,000 images from MNIST, and they're projected into a 2-dimensional space from a 784-dimensional space. And this takes less than a minute, way less than a minute, just kind of in our normal collab. Now, you may say, well, this is just one big blob. It's not very informative. We're not really seeing anything. But of course, as you take examples or samples out of the different parts of this big block, you will have different groups of our digits. And in fact, since for the MNIST data we do have the labels, we can superimpose this information onto this PCA, which is shown here in an unlabeled way, because we were saying PCA is for unlabeled data and it's an unsupervised technique. But let's cheat now and show the labels. And here you are. It's quite interesting. So the groups get actually quite nicely separated. 0 here, 1 over there, 2, 3, clear clusters, and a bit of mixture in 8, 5, 6, and here 7, 9, 4. That gets messed up a little bit. And let's see how this fits with our manual grouping. And you can see here are the ones with a vertical line. Here are the ones that have a curve at the bottom. Here are the ones that have a curve at the top. So it's actually agreeing with what we did in our in our manual layout. Now let's compare this to the alternative to PCA, which is called t-SNE, the T-distributed stochastic neighbor embedding. TC proceeds in the following 3 steps. First of all, it estimates the distribution of the distances, of the Euclidean distances in the high dimensional space. So it takes points and their distances, and it creates Gaussian probability distributions for these distances. And then it places points in a low dimensional space and computes the student t-distribution for these points. And then it runs an optimization where it applies gradient descent to minimize the difference between both distributions. And it uses the Kullback-Leibler divergence as loss function, which is a well-known loss function from neural networks. And you've seen here also gradient descent also is reminiscent of neural networks. So although t-SNE is not a neural network itself, it's very strongly motivated by work in neural networks. And in fact, Geoffrey Hinton, who receives the Nobel Prize for neural networks, is also the inventor of t-SNE. Now t-SNE runs in O of n square, and it captures local relationships quite well. It can be optimized. There are implementations that manage to bring this down to n log n. And this is what t-SNE looks like on the MNIST data. However, we didn't consider 70,000 because 10,000 took already over 2 minutes, and we have quadratic growth rather than linear growth, so I didn't even try 70,000. So what you can see is clearly nice clusters, 1, 2, 3, 4, 5, 6, 7. Okay, not 10, but that probably has to do that these big lumps here are aggregating multiple of the digits. And let's do the same here. Let's superimpose the figures, and we see it nicely separates, and the big blobs here is 3, 5, 8, which clearly are close to each other, and that makes sense. And 9, 4, and 7 over here, which overlap a little bit. And again, Similar to PCA, also here the layout in general agrees quite nicely with what we did manually. Curvy at the top, curvy at the bottom, and vertical line over here. And in fact, what must be said, the big advantage of t-SNE is that it clearly shows boundaries here for the clusters, which were not visible in PCA, that just gave us a big blob. However, of course, we have a lot of overplotting, and if in PCA we would add density information, we'd probably get similar cluster centers out as we clearly see here. So let's now come to the two competing methods from clustering. And in clustering we have two main methods, k-means and hierarchical clustering. And the key difference is that k-means requires a fixed number of clusters that we have to predefine, although we may not know how many clusters there are in our data. And the big advantage is k-means is really a simple algorithm and just requires iterations linear in the number of items that we have to deal with. Hierarchical clustering, on the other hand, as the name suggests, creates a hierarchy of clusters. And in the naive case, its n-cube complexity can be improved for single linkage. We will see in a minute what that means. Single linkage, so for this configuration of hierarchical clustering and with optimized data structures, it can be brought down to n square. And for complete and average linkage to n square log n. But the naive implementation does have n cube complexity. Okay, let's start with k-means. And the basic idea for k-means is that clusters have a representative. And items are assigned to the cluster by comparing it to the representative of that cluster. And after an iteration in which we assigned items to the most representative to the closest representative, after doing that, we have created a cluster with an existing representative, and now we update that representative, because after assigning the items, the representative or the best representative for that cluster might be a different one to the one that we used in the first place. So let's formulate that a little bit closer to pseudocode and then ultimately Python. So we start off by randomly picking k items as initial cluster representatives, and it doesn't really matter what we pick. And then we run I iterations. That's the caveat. We have to fix how many iterations. So for I iterations, we go through all of the n items, we go through all of the k cluster representatives, we compute the distance between the item and the representative, and then after having seen for an item all of the cluster representatives, we assign the item to the cluster of the closest representative. And after having done that for all of the items, we pick each of the k clusters and we compute the average of all the cluster members, and that becomes our new representative for that cluster. And then we continue with the next iteration and with new representatives. The complexity of k-means is I iterations times n items that we're dealing with, k clusters that we're dealing with, and since we're computing distances, we have to consider the dimensions. So that's the dimensionality of the data. Now, since n is typically much larger than I, k, or d, it essentially means that k-means is linear in n. And a typical setup for example, MNIST would be that we're dealing with 70,000 examples or 60,000, that I is maybe somewhere between 10 and 100 iterations. K, we know it's digits, so we pick 10 or maybe 15, so I have a few more clusters, extra clusters, that maybe the tricky cases can go into, and the dimensionality was 784. So basically n is way larger than these three, and that means it's fair to say that k-means is a linear technique. Now, the advantage of k-means is very simple, very fast, but the disadvantage is which distance measure are we using? Euclidean distance or some other specialized distance for our data? How many iterations we have to choose? How many clusters? What if we have no idea whatsoever how many clusters there are? And what we generate is not globally optimal. It's basically locally we take decisions, we assign, we reassign cluster representatives, so we cannot give a global guarantee on optimality of the assignments. So k-means on MNIST. The results you see here, I took 60,000 MNIST images. I ran 100 iterations, configured it with 15 clusters. I gave it more than 10 to basically create a way for tricky cases. And what you see here are the cluster representatives. So these are the 15 clusters in no particular order. It's not ordered by confidence or size. But this is the cluster representative. So this is the average for that cluster. And just in comparison, so that you can judge how good or bad these averages are, this is the average over all of the 60,000 images. And you see it's just blurred. There's white in the middle. You can see some curves and stuff, but it's not one particular digit. Whereas here you can see clearly that looks like a very clear 0, pretty clear 1, clear 1. This one doesn't look perfect. This one may be between 9 and 4 and so on. But by and large, some very striking results in terms of those, or some striking visual impressions of those averages of the clusters. Now let's do the same here. We do have the labeled information with the true labels. Let's evaluate it. And what is shown here is basically those cluster representatives. And the first digit here is going from 0 to 14. So those are the cluster numbers. So 15 clusters. Then you have the most frequent label in the data, and the percentage is how many percent of the cluster members did basically have this label. And you can see some pretty striking results. So for example, that 0, where the average is so clear, 89% of cluster members are 0. Here, even more, 95% of these cluster members are 0. This one also very good, 80%, 72% for this one over here. But you also see some lower digits, so indicated by the red arrows. 5 clusters have as most frequent label a label that occurs in less than 50% of the cluster members. And you can directly see from the average, yep, this is probably sitting somewhere between 3 and probably 8, or maybe also 5. This is probably between 9 and 7, 9 and 4 over here. Yeah, you have the 46% are 4, so it means the others will probably be 9. So overall, 10 clusters that seem to be very, very coherent, and 5 clusters which are somewhat in between. Okay, so let's turn to the second technique out of the clustering techniques that compete with the dimension reduction, and that is hierarchical clustering. In hierarchical clustering, we iteratively merge 2 closest clusters, and we update the distances of the newly formed clusters to existing nodes and clusters. So here you see a depiction of 50 of the MNIST digits, and using a technique of complete linkage, and in a minute you will see what that means. And as you can see now, because of that hierarchy, if we wanted to say 2 groups, we would cut over here, and that means we would have this group and that group. Let's say 10 clusters, so that means 1, 2, 3, 4. At this level it's 1, 2, 3, 4, 5, 6, 7, 8. So if we cut somewhat over here, we're like at 10 clusters. And you can see, okay, here zeros were grouped together, 2s and 3s, 1s, over there 6s, and so on. So you see already some grouping. But you also see that for visual inspection it's pretty tough. That doesn't look so nice and easy interpretable, and this is just 50 data points out of 60,000 or even 70,000 if we take the complete data set. Now let's see how hierarchical clustering works. So the input are pairwise distances, and the output is a tree with all of the nodes. So let's assume that we have this data given, A, B, C, D, E, and these are the distances, 2, 6, 10, 9, and so on. And this is the tree that we want to generate. A and B are closest, D and E were also close, next came C, and then finally those 2 branches get merged together. So let's start. In the first step, we're going through this distance matrix and we find that the shortest distance, and hence the pair that should be grouped first, is A and B at a distance of 2. All other distances are larger. So we group together A and B and create this new cluster, visually depicted over here, and we must now decide what is the distance of this new cluster to the existing nodes. So there was no cluster AB, so per se there is no obvious distance between AB and C. So what we do is we consider the distances that A had to C and that B had to C. That was 6 and 5. And then based on these two pieces of information, we make a choice what the new distance is. And here are choices. We took the minimum. And that is called single linkage. So we make it 5. So we're optimistic, if you will. And we give credit to A that was closer to C, and that becomes the new distance of the pair of AB. And something similar happens here with all of the other values, and those 4, 5, 3 didn't change. They were not affected by this grouping. Now we pick up the next closest, and that is 3 over here. D and E get grouped together, and we create this new cluster, DE over here, and it gets a distance of 8 to AB, because 8 is the minimum of 8 and 9, and 4 to C, because 4 is the minimum out of 4 and 5. So these two clusters exist now, and now the question is what happens next. And now we find the next closest is C to D and E at 4, and so we merge the C to D and E, create this new root, and that means we have now only 2 clusters left, A, B, and C, D, and E, and they have a distance of 5 to each other. Because A and B had a distance of 5 to C and of A to DE, minimum is 5, so that is the remaining distance. And so finally, in the last step, we create everything, put it together, and that becomes our root node. So in terms of pseudocode, the algorithm looks like this. We have M entities. We have in the variable U a set of current trees. Initially, it's 1 tree for each entity, and D is the distance between the trees in U. And we start off by initializing U as the set of clusters, each with 1 node in it. So for each entity, we create 1 cluster with 1 node in it. And while the size of U is greater than 1, we pick UV, the roots of the 2 trees in U with the smallest distance in D. And we make a new tree with a root W and U and V as children. We calculate the length of the edges for layout between V and W and U and W. And now for each root X in U without U and V, we do the following. We calculate the distance between X and the newly created W as the distance between X and that new node. For that, the so-called linkage method will come into play, which I'll explain on the next slide. So after processing U and V, it means we can remove them from our set of clusters we still have to deal with. So from the existing to-do, we remove U and V, and we created a new W, and that one gets added. So net, we reduce the size U by 1 by first removing 2 and then adding 1. So in sum, 1 is removed, and that means this while loop iterates exactly in the amount of entities that we have. Now, what does the 2 linkage methods do? So if we form a new cluster and we create that new node W that merges U and V, then we have to update the distances between other nodes X and the new node W that we introduced. That is not defined per se. And in single linkage, we take the minimum of X relationship to U and X relationship to V. And if you consider this very simple example, 3 nodes, A, B, C, A to B, and B to C have distance 1, A to C has distance 2. And so the distance between A and B to C, in this case, is 1. In complete linkage, we take the maximum instead of the minimum. So we have, in a sense, the pessimistic view. And then in our example, AB, the new node AB to C would become 2. In average linkage, also called WPGMA, we take the average out of those two distances. So in our case, distance of AB to C was A was 1 and B was 2. Sorry, A to C was 2 and B to C was 1. And so the average is 1.5. Now, average linkage is called WPGMA, and that stands for Weighted Pair Group Method with Arithmetic Mean. So why is this called weighted when there are no weights? We just take those two values and average. Why is it called weighted? And the reason why it's called weighted is that those two trees, U and V, they may have very different numbers of nodes. U might be a very large tree that has already 100 nodes in it, and V just a tiny tree of 2. Nonetheless, we treat both values as of the same order, and we just average them. And that is why, although you do not see any weights over here, it's nonetheless implicitly it's weighted. And that's why it's called WPGMA. Why am I saying it? Because there is an alternative method that is called UPGMA, unweighted pair group method using arithmetic mean. And the unweighted method is actually using weights, so that's pretty confusing. So what it does, it's using as weights here the size of the nodes in the cluster. So if U has many, then it also gets multiplied here by a large weight, and if V has few nodes in it, it gets multiplied only by a small amount of nodes, and then you divide by MU and MV. So although you introduce weights over here, what the weights actually do is that they remove the size differences in U and V, and that's why the method is called unweighted. As I said, a little bit confusing, but I think with this explanation you get the reasoning behind the naming. And let's just exercise this quickly, that this really makes a difference. Let's have the tree D with 1,000 nodes, and that means MD is 1,000, and E just has one node in it, so ME is 1, so we make it pretty extreme. And let's say that the distance of D to E is, in this case here, let's just consider that D to E is 1, D to F is 2, E to F is 98. So it's, of course, a constructed example. We create really a huge difference here in the distances. And now we group together D and E because they had the shortest distance. And now the question is, what is the distance of DE to F? And for the WPGMA, where we just build the average, we take the value 2 and the value 98. 100 divided by 2 means 50. And so that is when we treat those two values just as given, completely ignoring how many nodes are in them. But if we do the UPGMA method, we say, well, the short distance of 2 was the result for 1,000 nodes, whereas that big distance, 98, was only for 1. So clearly that 98 is a huge outlier. And through adding these weights and putting here 1,000 plus 1 to normalize at the bottom, we see that it nearly averages to the majority 2, so we got 2.09. And probably in this extreme case, UPGMA is much more sensible, and in that sense, it is more robust to outliers than WPGMA. So let's quickly see here in an example, it really does make a difference. So here, a calculation for one example is taking place, and in the UPGMA case, the distances amount in the end between AB and CD and E to 7.67. And if you did this for WPGMA, it would be 7.825. So again, these are maybe only marginal differences, but in fact, it does make a difference how you apply the linkage method. Now, the choice of the linkage method is, of course, a bliss, but it's also a curse. It gives you freedom that you can choose, and depending on your data, you can play with the different linkage methods. But of course, it's also kind of a curse because it can make a huge difference to your tree. And it's actually not the case that the topology of the tree stays the same, that it's basically just maybe the branch length or something that changed, as we saw on the previous slide. It's really that the topology can change. So consider this example of A, B, C, and D in 1, 2, 5, 4, 5, 3, these distances given here. If we apply complete linkage, then we get this balanced tree where A, B get grouped, C, D get grouped, and then both get merged. But if we apply single linkage, then some kind of chaining is taking place. Then A and B get merged at a distance of 1. And then since A had a distance of 2 to C, that get chained up. And only then in the final step, D gets merged. And that also is seen very favorable because from C it just has 3 as distance. So those two trees have the same amount of leaves here in the same order, but the topology of the tree is actually different between those two choices. So hierarchical clustering, pros, it's very widely used, it's easy to understand, it's a visual method, doesn't have any parameters like the number of clusters, but it comes with a caveat. You have to choose a distance measure, it has to be appropriate for your task. You have to worry about which linkage method to use. The complexity is, in comparison to k-means, very high, and the visual representation of large data sets is challenging. So here we summarize the differences again. So PCA, t-SNE are both dimension reduction method, k-means and hierarchical clustering are clustering techniques. Here are the complexities, and for simplicity I ignore any additional parameters like I and k for k-means and the dimensionality that was playing a role, and the dominating factor is always n, and you see here those are the numbers given, and for the n square and cube things can be done with clever data structures, but essentially PCA and k-means are the fast ones, and t-SNE and hierarchical clustering are the slow ones. Now, one more criterion to consider here is popularity, and that is a bit my own view. I double-checked that with biomedical publications. I just did a keyword search and looked at the amount of papers that I got, but just also from my experience in my field, PCA is the most widely used technique. Hierarchical clustering is the second most widely. I find that surprising because of that complexity. K-means is the least used, although it's so nice and fast. And t-SNE ranks on third rank. And just to emphasize that again, that they have all of these algorithms have this in common. The key thing is about them, they're unsupervised methods. They do not require any training data. And the key distinguishing features are PCA is a linear transformation, t-SNE can handle nonlinear data, k-means is simple, but it has this parameter k you have to deal with, and for hierarchical clustering you have to deal with the linkage method. Now, to conclude the lecture as a final note, the really ingenious thing in neural networks was the introduction of autoencoders because they are unsupervised. It's really difficult to get by training data. And as impressive as MNIST may be, and ImageNet with 15 million classified, categorized images, getting accurate labels for data is very, very difficult. So the idea of autoencoders, as we discussed them, was that you train a neural network and you actually repredict the input itself. That means you do not need any labels. So when I show these two pictures, the neural network has no idea that this is a 9. There is no ground truth, no training data where labels were given already. It's just a picture, and this is a picture. And the key was this bottleneck that is in a way a dimension reduction that that is taking place here. So in that sense, an autoencoder can be considered an unsupervised method that carries out a dimension reduction, and the reduced dimensionality is actually over here at this bottleneck. And that is really ingenious because it all of a sudden means that these autoencoders have incredible amounts of data available because you do not need any labels. And that means the big companies who have this data, they can run their autoencoders over billions or even trillions of photos that we have uploaded on WhatsApp and Instagram and so on, and the likes of Google, that it can apply this to all of the web contents, right? And these are in a sense data corpora that of unprecedented size, and because of this unsupervised technique, they are amenable to these autoencoders. And a second note, there's one technique that I don't go into, or that I didn't include in the list of 4 that we did in this lecture, but I still want to mention it so that you have heard the name, because it's a very, very nice technique. It's closely related to PCA, and it comes from statistics. It's very old, but it's easily explained as called multidimensional scaling, MDS. And essentially what multidimensional scaling does, it tries to find points in low-dimensional space that satisfy high-dimensional distances. So PCA was taking the high-dimensional vector. MDS takes high-dimensional distances. Now you may say, well, what's the point? That is not a huge difference. But in practice it can, because sometimes we do not have the high-dimensional data, but we just have the distances given. And this is also beautiful because sometimes we do not have the complete data available. We do not have the distances between all objects, but we only have some distances. We only have a graph specified. And essentially finding the low-dimensional points in the low-dimensional space corresponds to creating a map. And a nice example for what MDS does is taking a distance table, so this is a historic picture of distances in miles between Dutch cities, and you see here on the top is Amsterdam, and somewhere over there is Maastricht, and Groningen is there. And with these pairwise distances, you should be able to draw a map. You know, maybe not with the boundaries and the coloring, of course, but with the cities placed properly. And if you do that, what MDS is basically creating is taking information such as Amsterdam has a distance of 44 to Groningen, Groningen has a distance of 63 to Maastricht, Maastricht has a distance to Amsterdam of 40. So multidimensional scaling gets these pieces of information, and it then places the points in space to basically mimic these distances. And as I said, it's a nice technique because here in this case of pairwise distances, you do have complete information. So this table does actually provide all of the distances. But there will be cases where this is sparse, you know, where you only know about some relationship and others you don't. And then these techniques, which really amount to graph drawing techniques, are really quite nice to handle the sparse data. And that is then something that the other techniques I showed you cannot handle. And that makes MDS a really beautiful technique to work with. So take-home message for today. You should understand the difference between unsupervised and supervised. And you should understand the principles of dimension reduction and clustering. You should understand the pros and cons of the 4 techniques that we discovered. And in particular, you should be able to answer questions like why minor dimensions in PCA can be relevant, how gradient descent is being used in t-SNE, and what the different linkage methods in hierarchical clustering do.